There's only 5. There's 6 of us?
Jesse and Kayla are missing.
Kayla. But I don't think Kayla comes to class on Fridays. It's kind of a thing she looks
No, she doesn't come to class at 8 o'clock in the morning, so she doesn't do. All right.
Neither. If I was Kayla.
Keep that in mind. Maybe I'll
I'm not though.
schedule dynamics next semester at 8 a.m. or something.
You don't want to. I'm getting a haircut, by the way, just to make you happy.
Really?
Mm-hmm.
That's why you're getting the haircut?
That's why it's funny. And because I show like a dog, this hair right now.
Getting it cut handsomely?
Fancy. Something.
No guard, just straight clipper, man. Just straight.
I've
clipper.
done that before, and it's
Way to go. All right.
There's nothing like it.
Today we're going to go beyond statics.
Beyonce.
So we're everything we talked about there is Kayla.
Hey, it's great to see you, Caleb. We didn't think you were coming to class.
No, Colin didn't think you were coming to class.
You
I knew it
surprised us
wasn't. It was not an 8 o'clock class, and that you would be here. So I knew. All right. Beyond statics. So let's consider this situation. Jesse,
Hey, how's it
glad you could join us. All right.
Me too.
Oh, don't let me forget you three about the.
Yeah, I had a question about it. Do you just need our hours, or
I need just how many hours you have booked for next spring?
I have no idea. Well, I haven't booked yet, but I planned
Plans. Okay.
15 or 16.
15 or 16. You know.
Gonna try to do 17.
You try to do 17.
Yeah, maybe 14.
You have 17
Maybe
on your
14.
schedule, but on your tentative schedule right now you have 17.
Yes.
Okay. And you don't know.
I want to do 16. That's
16.
what I want. That's
Yeah.
what I'm gonna try.
Your plan is for 16.
Yes.
But you don't have specific classes
No, I
identified.
don't have specific classes.
Okay, but you have specific classes identified for your 17,
Yeah.
and you have specific classes identified for your 16.
Right, 15, and then one, I might, it's a 1 credit hour. that I
Oh,
might-
right, okay.
I have
All right.
14 planned.
Why do you need that?
Because we're trying to figure out, we're gonna make a change to junior project.
Oh.
At some point that will move it to 3 hours, but from the 2 hours that it is now.
Okay.
But that means that everybody like you and Josiah and Cassidy, you have 17 next, you don't have 17 on
Oh,
your.
no, I don't even know.
You,
I just love
so
how
you,
I'm
Josiah, and
just kinda-
Cassidy all have 17 planned for next semester. So if we moved it to 3, then it would be 18 for the 3 of you. So we've got to figure out if we should wait until the next year or whatever. So anyway, that's what we're talking, that's what I'm figuring out. All right, beyond statics. So let's take this situation here. And we'll apply a force P in the center. Okay? Everybody understand the problem? Okay? This is what you learned in statics, hopefully, as being statically indeterminate. Everybody remember those words?
You were right, that's the thing.
Okay. So what that means is I need to find the reaction forces, right? So I have this applied load. So what are my reaction forces in this case?
The reaction conjoined against the member. P unit.
Okay, what, give me a direction
FX.
Negative X direction.
in the X direction. Okay, so we have a, let's call this A, and this is point B, and this end is C, so we'll call that C sub X.
You also have a force at A in the negative X direction.
A sub X. Okay? So I have two unknowns, but only one equation. They're collinear forces, so there are no moments. Right? They're only in one axis, so there's no second axis. So I have a statically indeterminate. It is, I cannot determine, it's indeterminate, I cannot determine what the unknown forces are, the reaction forces. Right? Best I can get is I can get sum of the forces in the X is equal to P minus A minus C equals 0, or AX and CX. Right, two unknowns, so I need another equation. Right? So now that we're talking about strength of materials and acknowledging, in fact, this is not an ideal material, it does deform. Right? This bar in the center here can deform. What is the deformation of that bar?
Y direction, right? So it's
Well,
okay.
we're on, no, it's a one dimension problem, don't worry about the one. What's the deformation in the x direction? I'm asking for a number.
Oh, we don't know.
Yes, we do.
0.
0. It's constrained. You get rigid constraints on both ends, right? It can't elongate. It's fixed on both ends. Okay? So that the deformation of section AB, that little section, plus the deformation of section BC has to add to 0. Now you can imagine if this was a piece of rubber and I pulled on it, what's going to happen?
It's gonna, there's gonna be some massive shifts in the direction of P.
Right, the hole is going to shift in that direction. This piece is going to get longer, this piece is going to get shorter, but the total change of the whole thing is 0. Does that make sense?
Would we able to change the volume?
You're just the king of it. I want to know about the volume.
I'm just curious.
We'll get to the volume later, just check. You're not worried about the change of volume. Yes, but what are the quantum mechanical implications of this? Anyway, so when in doubt, if you're trying to have difficulty visualizing these things, it's oftentimes easy to think of it as a piece of rubber. Because rubber is something you can deform with forces and has significant deformation you can visualize. We don't think of this steel bar as deforming, but it does. Right? Steel bar behaves no differently than rubber does, except that the modulus, the elastic modulus, is just really high modulus. Okay? But the general idea is still the same. So, what is the elongation of section AB? How would I find the elongation of section AB? We did this last time. What's the method that I would use to find the elongation? I would do a method of sections. Where would I section? Just to the left or just to the right of B? If I'm trying to find the left hand. Just to the left of B, right?
Wait, which side are you looking at first?
I said I'm AB, section AB,
Oh, AB, okay.
this chunk. So I go just to the left of B, so keep P out of the equation. I only have one force, and then that deformation is AX times LAB divided by AE, and it's uniform bar, so I'm just going to call it AE, not specify the AB subscript. Okay, does that make sense? Because in that section just to the left, if I take just a section of the AB, the only force acting on it is AX, so there's a reaction force here, an internal force there, AX, and a normal force. And it's just a bar that's being pulled with AX, and so the deformation is AX LAB over AE. Similarly, deformation from BC, for BC, is what? So we're just talking about this piece. And so I'm just going to take the BC piece. What forces are acting on the BC?
P and CX.
Hmm?
BC, P, and CX.
Yeah, except that we're taking infinitesimally to the right of P, out of the center now.
So just C.
So just CX. So what's the internal force on this end? Well, easy. What is it?
What's
CX. Right, so CX on this end as well. Right, so because we don't worry, as long as we take an infinitely thin slice here, a finite but very narrow slice around B, so that P is never applied on either system, it's okay. Right? because that can, the thickness of that slice can go to 0. We don't have to worry about incorporating P. Okay, so what is delta BC then?
LC times LBC over AE.
So what was it times LBC?
CX. Negative.
Negative, good. I didn't have to ask it, it's my next question. So
Well, is it,
Compression.
oh, is it just a minus because?
why is it
compression-
minus?
Compression?
Because it's in compression. All right, so now we have the total, so now we can add those two together. And so we know that AX LAB over AE minus CX LBC over AE is equal to 0.
Hey, can I just take a minute?
Yeah.
What is the proper terminology for E? Is it is it, is
Elastic
elastic?
modulus or Young's modulus,
Okay, so elastic modulus.
that will be fine. I mean,
So it's just a number representing how stretchy something is?
it's the slope of the stress strain curve, yeah.
Oh, it's just, okay.
Because most everything we do, we assume we're behaving in an elastic regime. We don't want anything to plastically deform, to deform beyond, coming back. And if we do, we deform it, and then we put it in the system, and it behaves elastically up to that. Remember, we talked about it, but once it's been strained, we have the strain hardening, so that it's still, we're working in that elastic regime. Okay. So, this is a thing, AE, we can cancel out the AE because it's the same for both ends of the bar. And we're left with an expression then for AX in terms of CX, LBC over LAB times CX. And if I come back to my original sum of the forces and solve this for AX, that has to equal P minus CX. Right? So I've got two CX's in there. Let me rearrange the right-hand side of this equation. Well, I'll just skip to the end. You can go back and do the algebra you want. CX then is going to equal P times LAB over the total L. And AX is going to equal P times LBC over the total length. And you can see that in here by adding this, when you move the C over here, you end up with 1 plus this. 1 plus LBC over LAB, which is the same thing as saying LAB plus LBC over LAB. Anyway, the point is, you get this kind of relationship. For those of you who've had material science, it's an inverse lever rule kind of behavior. The force, looking back at the force C, is the force P times this length, the opposite end of the of the member divided by the total length. Everybody see that? So to find the force on the right side, I take the ratio of the left side divided by the total length times the applied force. Yeah.
I may be getting a little picky, but I'm still stuck on why we were able to just kind of poof, eliminate P from our two.
Because
equations.
we're looking at the deformation of the bar.
Okay.
Okay? So essentially what we've done is we've come in here and said we're going to ignore this little piece that is so thin that effectively it has no deformation at all. It's so thin that whatever P applies to that thing is negligible. Right? If I take a piece of paper and I pull on it top and bottom, it's the total elongation of that piece of paper is essentially 0, right? Through its thickness. So all the elongation is stored here and here.
I mean, if I'm thinking about a bar with force on it, and there's force applied at a specific point, is this theoretical, or can I actually model something real using this?
What do you mean?
it seems like we're cheating, using, like, just pulling P totally out of the equation.
No, we're not cheating, we're just, that's because if we keep, well, we could do it with P in there,
Just be harder.
right? But the math, we'd have, then in here we'd have a P pulling in this direction, a CX pulling in this direction, right? And then we'd have a P minus CX pulling in this direction. We'd be right back where we were to begin with. So mathematically solving for it would be difficult, right? If not impossible. Because we just have too many unknowns.
So the effects of P, the effects of the force of P are contained in our CX and AX, right?
Right, yeah, right, because this is where P comes in,
Yeah.
right? So we're just trying to figure out what is the distribution of the reaction forces between C and A. And what we found is the distribution depends on the relative location of P, or the application of P. So if you think about it, CX is P times LAB over L. As LAB gets smaller and smaller and smaller and smaller, CX gets smaller and smaller and smaller and smaller. Right? But that makes sense. If P comes all the way down here, then I'm going to get a huge response from this thing and not so much down here. Right? You can kind of sense that it's a piece of rubber. Right? If I'm pulling on a hole that's right here, the real stress it's going to pop right here. Right? There's all the stress is going to be placed here, and there's not going to be barely anything felt down there. Does that make sense? Yeah.
I guess the only other thing I would ask, this is kind of getting a little bit out there. We can do that for that one force in the middle, and I understand that now. But what if there are, say, like, we have two forces, like we say we have two holes like that? How does that change the dynamic of how we go against that? Because
Right, so in the simplest sense, it changes the dynamic because you have to do the analysis twice and use superposition.
Okay.
Right, because that's how superposition works. Right.
Okay, so
I mean,
it's still hold.
You could do the same thing straightforward, you just end up with more terms and more equations. And you'd end up with something for CX that is the sum of, so CX is essentially going to be P times LA, so in other words, if I have a point D in here with another force acting on it, then CX is going to be P times LAB over the full length, plus whatever force this is, F. F times LAD over the full length. Right, so superposition. That's where we'll end up in the end.
Okay,
Okay.
that makes sense.
Okay. That's why superposition is particularly helpful. In fact, we can use superposition to go back and do this analysis. Let me take that off of there. We can use superposition to go back and do the analysis in the first place. Okay? So we've got that the delta of the whole thing is equal to 0, is equal to delta due to P minus delta due to C. Right, so if we look at this picture, I can break it apart into the two ends, so I can geometrically break it apart, or I can break it apart into the displacement due to P and displacement due to C. Because AX, and I'm measuring all my displacements relative to this fixed barrier here. So AX does not contribute a displacement, right? It doesn't. There's no strain due to there's no strain due to AX, because that would be delta over L naught, and L naught for AX is 0. Right? Because I'm starting out right here, where the force is applied. So the only forces that cause an elongation are P and C. Yeah.
Going back a little bit, could you do the algebra real quick, or just say what you did for AX going to?
So I essentially moved the C to the other side. Here, I'll just do it real quick. Therefore,
Sorry.
P is equal to CX plus LBC over LAB times CX, which is equal to 1 plus LBC over LAB times CX, and 1 becomes LAB plus BC over LAB times CX. The numerator is just the total length of the bar. So then LAB over L as opposed to L over LAB when I move to the other side. Follow that? That's what you want to see?
Yes.
I guess. Okay. So the bottom line is these are the two expressions. Now, if we do it in terms of the forces, so when I do it this way, I first look at it as if it is a bar with no constraint at the end and just force P pulling on it. So delta P, delta due to just P, well, there's no extension in this end at all, right? Because it's not experiencing any force in this configuration. So delta due to P is just the force P times the length of which it acts, AB over AE. Okay, see that? Right, so essentially I'm just pulling on this little section, and that's just dead weight at the end. Similarly, I can draw the same thing, but now I only have CX acting, and P's not there. So delta due to C is equal to, I put the minus sign in there, because I know it's compression. Actually, let's just leave that as a plus, and then I'll put my minus sign in down here. So delta due to C is CX, the applied load, times the full length of the bar, right? Because in this case, CX is compressing the whole thing, divided by AE, but because it's compression, it's negative. So now, then what I end up with is I end up with P LAB minus CXL is equal to 0. Getting rid of the AEs because they're the same. Move to the other side. CXL is equal to P times LAB. Dividing through by L, CX is equal to P times LAB divided by L, which is what we had before. So either approach works. Superposition or the treating, geometrical superposition or load superposition, both arrive at the same result.
Why were you ignoring A again? For there?
Because A is applied here, and this is my 0,
Okay.
so there's no length, there's no initial length for A. So, again, it's sort of like the piece of paper. I can push on that all I want, but I'm not getting any displacement on it.
Mhm.
Okay. How do you feel about that? Clayton feels okay. Not everybody else. You guys with me? Okay, we're kind of put on the spot then. Last person to say yeah.
Not me.
Not you, okay. All right. So effectively, we just need to understand this fundamental rule. That it's all about the contribution from the reaction forces, or the magnitude of the reaction forces, is the total load applied, normalized by the opposite end. The ratio of the opposite end. Okay. All right, so, and then by sum of forces, you'd end up with the AX expression in that equation, if you did sum of forces. All right, so let's look at a, I always forget to turn this thing on. I have too many electronic things that I gotta do at the beginning of the class.
Thank you.
Such
What's
a
that?
first world problem.
Yeah.
Too
Do you have an
electronic.
XKCD for us?
What's that? Somebody said something?
Like,
Do you have an XKCD for us today?
An XKCD for you. No, I do not have an
Darn.
XKCD for you.
That was Dr. Davis.
Yeah, I know.
He's just really hoping that every class. anything
Yeah,
you let down-
now after Davis showed that one, I just kind of want it to just be integrated into my.
Cartoons all the time, every day.
log on to CSC computer that had SVCD back in the day?
Oh, I
Hello?
don't have anyone.
You can do it.
Oh, come on, don't tell me my,
Yep.
Hey, you're a hacker.
shoot. Really, the
Yeah,
battery's
get
not
it.
on this thing?
Like a,
Lick 'em?
yeah,
Yeah,
like
yeah. We got like a
What kind of
bunch
battery?
of computers in a van, it's not hooked up to
Triple A.
anything, just sitting in the middle of the road, hacking everything.
Everything.
My fear is that's not the problem.
what, yeah.
What, batteries?
Battery, yeah, the batteries is not gonna be the problem.
We,
Some sort of.
we could see how much
Build an antenna.
Ah,
strain would go on the keyboard if we threw it down the balcony.
Ooh,
What?
I like that idea.
Check out the plastic.
Do what?
Plastic
You wouldn't
keyboard.
do-
I was focusing on the classroom material here, I'm sorry.
That was classroom material.
Yeah,
We wanna see how much strain it takes, what?
if you throw that off the balcony, how much strain would it would
Experience?
Yes.
Yeah. Yeah.
What- Specifically
can
when it hit
measure
the floor.
Yeah, only if you had a good way of instrumenting it to measure.
So how would you measure that in would you do like a high-speed camera
Accelerometer.
on the,
You measure you measure the force. If you actually want to measure the strain, it's gonna break, so there wouldn't really be strain to measure. But strain gauge, if you were really measuring the strain, like you had a hunk of steel or something, you want to put it down there, you could put a strain gauge on the side, which is a piece of resistant metal, so that as you compress the metal, you change its resistance. As you stretch the metal, you change its resistance. So you can measure them. All right, we're back up. All right.
Yeah.
I think we should do a tensile test on the keyboard. See what happens.
What chapter are we in? 4?
You chatted
Yep.
to me whatever.
Yes.
I
Okay.
was wondering why I saw all those awesome words with your voice coming out of there.
That's not electronics.
All right, so we're gonna do the first one up there at the top.
Pretty much what it's.
Steel pipe is filled with concrete, and we're gonna put a load on it.
Says it sounds delicious to you.
Yep. It's like a donut.
Compressive force of 80 kilonewtons. Brace. Determine the average normal stress in the concrete and the steel due to the loading. The pipe has an outer diameter of 80 millimeters and an inner diameter of 70 millimeters. And then there you have moduli for the pipe and the concrete, for the steel and the concrete. So what's the first thing we're going to do?
Can we go free body?
We need a free body diagram. Okay.
Glad Blake's back in class.
Yeah, we had a channel you last time.
I'm gonna take free body for
I channeled you from your sleep.
The daily double.
Thank you, Blake.
Okay, 80 kilonewtons. So, pretty straightforward free body diagram, right? Not much to it. Force on both ends. And we want to find out what the average normal stress in the concrete is. Okay, because it's and then how much is in steel. So, what's in the last example that I gave in class here, I said delta was equal to 0. Is delta going to be equal to 0 here? No. So we can't say delta equals 0 equals A plus, delta A plus delta B. So we're going to have L delta C, delta of the concrete, and delta of the steel. And they're not going to be 0. But what do we know? About these deltas? Think about it. Should be equal. They should be equal. So we can solve this by setting the displacements equal,
Why should they be equal?
because they're bonded together.
Yeah.
Right? If I put a steel plate on the top, right, the concrete's not going to suck down and leave the steel up, because then there's not going to be any load on the concrete. Similarly, if the steel were to compress and the concrete didn't, right, they both have to move the same amount. Okay? All right. So, what can I do?
Is there any way we can operate on the 200 and the 24 gigapascals in order to make a singular E? And
There
treat-
is, we'll talk about that in material science.
Classic E.
For the time being, this is what you call an isostrain condition,
It's okay.
because they both have the same strain, same displacement. But we're not going to do that now. Instead, we're going to take a different approach. So I have, what is it I'm trying to find?
Average normal stress, concrete density.
Okay, well, I heard normal stress and normal force, right? Normal stress is what they're asking for. I'm probably going to want to solve for normal force and then go from there, right? So I'm really looking for P in the concrete and P in the steel, normal loads. Right? The portion of that 80 kilonewtons borne by each of them. What are you laughing at?
Hey, concrete?
I feel like I'm back in third grade.
Yeah,
P in the
you got that
concrete,
one.
P to the P!
Hey,
All
why
right.
not P?
All right, so what do I need? I need some equations, right? I have two unknowns. I'm presumably gonna need two equations. What two equations might I use? I kinda have one there, but maybe we can rearrange that one later, but go ahead.
You need two equations, one for each of the pressures?
One for each of the pressures, well, give me an equation. Well, no, we could have two equations
You
and
just
two
do
unknowns.
force times the area of the concrete and then the force times the area of the steel pipe.
Wait a second, hold on a second. So P of the concrete times the area of the concrete equals sigma. I'm sorry, no. You're saying sigma of the concrete times area of the concrete is equal to P of the concrete. And sigma of the steel times area of the steel is equal to P of the steel. Is that what you're telling me? Those are correct equations. Is that the equation you want?
I wasn't thinking about sigma, I was just thinking about probably something wrong, if those are the right ones.
So we have to have equations though, right? I mean, these are just redefinitions. We have to have two equations.
I was thinking it's force times area.
P is force.
Oh,
Right? P is the normal force that
I was thinking.
you can use P for. Well, yeah, I mean, the last example we used P. So, okay. First one's easy. Coming up with the first equation for our two unknowns is easy. What's the easy equation? Right, sum of the forces. Right? So P in the steel plus P in the concrete has got to equal 80 kilonewtons. Right, that's the total load being borne by the column. So we know that the force borne, the fraction of the force in one is 80 minus the fraction of the force in the other. So that's our first equation. Now we need a second equation. It's actually already on the board.
Expand our DC or DST.
Right. Expand our delta expressions. So what is delta C?
Concrete.
It is funny when you say it. P in the concrete.
Times length over the area times the modulus.
Okay. Any other subscription you want to put in there?
The area of the concrete and the modulus, modulus of the concrete.
Right, so the L is the only thing that's different.
Yeah.
And that's got to be equal to then P in the steel, L over A in the steel, E in the steel. So now I have two equations, two unknowns. I know A of the concrete, I can find it. I know A of the steel, I can find it. Right? And in fact, since it's asking for the normal stress in the concrete and the steel, I would look at this and say, oh, look here. That already is my normal stress. Right? So maybe what I really want to do is I want to write this as sigma C L over EC plus sigma steel L over E steel. And then just make sure I divide each of these terms, divide through up there. See what I'm saying? Okay. But for the time being, that's not the way my numbers are based on this. So I'm going to keep solution key has those numbers. So two equations and two unknowns. What's AC?
It's gonna be just pi, let's see, 35 millimeters squared times, what, 500 millimeters?
No, it's just the area of room.
Oh, yeah, sorry. Subtract.
Okay. I went pi over 4 times 70 millimeters squared. Okay. What's A of the steel?
It's going to be pi, I guess you can do over 4 times the 800 minus 700 squared. Or 800 squared.
Right? Okay. So I got the areas, the E's were given to me, the L's are all 0.5. I've got two equations, two unknowns, I'll just give you the values. Piece of steel equals 57.47. MP of the concrete is equal to 22.53. Is that what I got? Is that my answer? Yeah?
Does the, for the area of steel, does the square go on the inside or outside of parentheses?
It goes on the inside, it does, because it's the area of this one minus the area of that one,
Right, okay.
and those are both d squared.
I think they both negative.
Yeah, but the normal stress, we'll just have to specify at the end that it's a negative normal stress. I mean, everything's compressive in this problem, so
Gotcha.
you only have to put minus sign and you can get the line. Okay.
Now we divide by the.
And divide through by the two areas, right? So you take PC divided by this, and P steel divided by this, and we end up with sigma of the concrete is 5.85 megapascal, and sigma of the steel is 48.8 megapascal. Does that make sense? Okay. Yeah.
Where'd you plug in the area to find the P?
Just take this number divided by this number. It's load per unit area, which is the stress.
Where'd you get the P? I missed how you found P.
Just solving these two expressions. So I have two equations,
Oh, so
two
you-
unknowns.
Okay, so
Oh,
you just put it together and solve, okay.
Right, I just solved for them.
I was like,
Did this, you know. Right. So two equations, two unknowns.
go.
I don't think we really need to work through algebra in here. Hopefully we're
Okay,
we're
you never
okay
know.
with that. Right.
Just had to make sure.
You guys do know, you've all had math methods, so at least you know how to do how to solve multiple linear equations. All right. So we don't have to do that. Okay, is that good? So the point here is to show you that unlike the example I gave you in the lecture part at the beginning before we got to the problems, where everything was driven by delta. You know, it was a delta constraint. Here, we don't have a delta constraint, except that the two are equal, they're not equal to 0. Right, so in one case we have delta equals 0, here we have two deltas that are equal to each other. Right? So there you go, okay. Now, let's try 46, let's see how far we can get, we got 10 minutes. Okay. So we have a column, we have two columns, joined in the center by a mating plate, and then there's a little gap at the right-hand end. Ever see the little gap? Okay. The gap between C and the rigid wall D is initially 0.15 millimeters, barely more than the width of a human hair. Determine the support reactions at A and D when the force P on that mating plate is 200 kilonewtons, and it's made of A36 steel. The whole thing's A36 steel. Okay? And we're assuming that the columns are solid columns. You know, they're not hollow columns. You know, they're not pipes. They're columns. Okay. So, how do we do this? Well, here we can't say delta equals 0 because delta can be 0.15. Right? And we can't say delta of one piece equals delta of the other piece. So we don't have those constraints. So we're going to have to take a slightly, we're going to take one of two different approaches. Where are we going to start?
Could we do a free body of AB?
A free body diagram. Okay, you want to do it? Well, let's just do the free body diagram, the whole thing, and then we'll break it up if we need to.
Okay.
Okay. Okay, so we have. All right, and we have a P applied here.
Now, is that P on, is that on the mating plate, or is
Right,
it
so it's on the interface.
So it's not on column A, or
It's
column
on, they're mated together.
Okay.
So it is shared, you know, it's shared. It's no
Shared.
different than the hole that I had to be in. Okay, there's one B, one force. Any other forces?
Reaction force at wall A.
Reaction force wall A,
In the X direction.
minus X direction probably.
Yeah.
Let's call it A, because there's, again, everything's one dimensional. Any other forces?
And we're assuming it's not the weight of the.
Right, right away. There is one other force.
Here's a normal force on, at the mating plate for B, BC's pushing back on P.
No, because right now we got the whole plate thing. That's an internal force. And that's a pair of internal forces.
It's going to be the normal force of wall D when it touches.
Right. There's going to be a force there when it touches. Right?
Do we technically know it's gonna touch though?
Yes.
No, we don't know that it's going to touch, but if we find a negative value for a force, then we know that it didn't touch. So in other words, if we find that D in the configuration we've drawn, in the orientation we've drawn it, is negative, then we know, oh, it never touched. So when we solve for D, if D is negative, then that would means that to have achieved that condition where it reached the end, D would have had to pull on it to get it to reach there.
Gotcha.
Okay, and we say, oh, that couldn't happen.
Yeah, okay,
Okay.
gotcha.
All right. So there's the overall picture. So I'm going to suggest that we handle this one by superposition. Okay. Anytime you have this thing with it, oh, is it going to end? Is it going to touch? Is it not going to touch? It's best to handle it by superposition. Okay. And what we know then is that delta of the whole thing is equal delta of the force P plus delta due to the force D.
Just like we had before.
But now instead of that being 0, we know that that's 0.15 millimeters. So now we indeed break it up into the sections we were talking about now. So I'm still typically going to draw the whole thing. But in the first case, I'm only going to apply force P. Oops. And I'm going to say, okay, well, the delta due to P is equal to what?
force times the,
And P times the 600.
Okay, what's P? We have numbers for everything, so we put it in.
Oh, the 200 kilonewtons
So we have 2 times 10 to the 5th
times 600 millimeters.
times 0.6. Notice she only chose 0.6, not the whole thing, right? Because P is only going to stretch this left-hand end. It's going to have no effect on this right-hand end. Okay, go ahead.
Over the area. Is 50 millimeters squared times the modulus of a 36 scale that we can look up in the back of
Very good. What was the modulus of A36? It seems it was 29. Oh, no, that was in SI units, sorry. In GPA, it's 200. 200 gigapascal. So 2 times 10 to the 11. Keeping everything in SI units. Did they give me a value of delta P? Yeah, they don't break it down. Nets. They don't give me a value for it. Okay, whatever that number is. We're out of time. What about delta D?
Same thing, but
So now for delta D, we have the picture that looks like this.
We don't know the force of D. So because we need to calculate,
Right, so it's gonna be D, is gonna be our unknown. Because we're calculating reaction forces. D times what? What length?
so it's how many millimeters by 600 millimeters.
or I guess if we're splitting it up, we just want to do 0.6 meters.
D times 0.6 divided by what?
So small
By 4 times 0.025 squared times the same modulus 2 to the times 10
and then add the big portion.
Plus? Is that what you're saying?
Yeah, we said add the big portion to it.
Okay, what's the big portion?
The D times the by 6. And then the area of 50 millimeters times the same modulus.
All right, so now, the same load, D, acts on both halves. Right? It's compressing this piece and it's compressing this piece, and it's the same load. Well, on an axis like that, you have the load has to be the same at every point in the axis. Right? So this piece is experiencing a 600 or a D compression. And that's what this delta is. But this one's also going to compress. So it's got its own compression. So you have the total of both of them. We have to add this plus this to get the delta. One more thing is missing. What is it?
The delta D is negative.
Right. These two have to be negative because they're both compressive. Add those three together, we get 1.5 times 10 to the minus 4 meters. Or 1.5 millimeters. And there, if I add this minus this equals that. The only thing I don't know is D. I can solve for D. And once I have D, then I can come back up here and use some of the forces to solve for it.
And then you know everything.
Then I know everything. For what it's worth, D is 20.4 kilonewtons. And A is then 180 kilonewtons. So as you work through the problem on your own, should you choose to, you can continue to get those answers.
How did you say you did, B from the two?
That's the only unknown. I take this, and that's equal to that. And then I'm plugging these values in up here. The only unknown that's left is D.
Wait. But how do you, okay. Yeah, you add the two together.
I take this, minus this,
Yeah,
minus this,
you don't know D.
equals this, 1.5 times 10 to the minus 4.
How do you know that?
Because it moves by 1.5 times, it moved by
Oh,
1.5
okay.
millimeters.
Yes.
Yeah, it's all about the mojo.
Okay.
There were only 5 people.
No, there were 6.
1, 2, 3, Colin, Blake, Jesse, and you.
Jesse. 7.